Okay, let's go back to what we were talking about. So, like I was saying, if I say I want to make a voltage amplifier, this is our model. So I know I have some input resistance to it. I know I have some output resistance to it. And I have some gain. Built into my amplifier model, but I don't know how to make it. You can get resistors in the lab, but how are you going to get this dependent voltage source? We don't know how to make that. Okay, so the easiest way to realize something like a voltage amplifier is to use an op-amp. This is what's inside of a typical CMOS op-amp. And you probably don't know what CMOS stands for yet because I haven't gone over it. But it's the technology used to make these transistors. I haven't gone over transistors yet, so you don't know what these symbols mean either. But by the end of this semester, you will be able to recognize what is happening in this circuit. And if you go on to 326 after this, then you'll start working with a lot of these kinds of transistor circuits. Right now, this semester, we're going to be working with single transistor circuits. And when you take 326, you'll work with circuits that have more than one transistor. Okay, so you don't need to know what's going on inside the op-amp yet, but just recognize the fact that there's a lot of stuff in there, and that all of this can be modeled by this voltage amplifier model. We don't draw this schematic every time we want to make an op-amp, so if you haven't seen it before, this is the op-amp circuit symbol. There's a inverting input that's marked by the negative sign, a non-inverting input marked by the positive side. This is the output. And these two connections with the arrows are to connect DC power supplies to. That is what powers the amplifier. Okay, so let's talk about the ideal op-amp. So this is the perfect op-amp that doesn't actually exist in real life. But what makes having an ideal op-amp model useful is that even though real op-amps don't behave exactly like the ideal op-amp, it's pretty close. So this is a good estimate of how the op-amp will behave. And there are certain properties of this ideal op-amp. So I'm going to list some of them. Okay, so the first one is that the resistance going to any input terminal of my ideal op-amp is infinite. And that's also marked on this schematic diagram on the bottom. So if I look into the inverting input, that resistance is infinite. If I look into the non-inverting input, that resistance is also infinite. If I look at the output resistance of the op-amp, that's 0. So now looking into this output terminal, that resistance is equal to 0. The third property is something called common mode rejection. And the ideal op-amp has infinite common mode rejection. What that means is that if the voltage at one of my input terminals, so this one is labeled 1, so let's call the voltage at that terminal V1, and we'll call the voltage at that other terminal V2. If those voltages are equal to each other, then my output voltage is going to be equal to 0. doesn't matter what the voltages are. It could be V1 could be 1 volt, V2. As long as V2 is also 1 volt, then my output is equal to 0. Okay, so that's called common mode, or that's a common signal. And because the output is 0, what we're doing is we're rejecting any signals at the output that are the same at the input. We'll talk a little bit more about this when we talk about non-ideal op-amps. The other characteristic is that the gain of this op-amp is infinite. And this specifically is open loop gain. So if I put some input at the some signal at the input of my op-amp, ideally I get infinity volts at the output. Now that doesn't sound reasonable, but that's because we never use the op-amp in that configuration. And then the last one is that bandwidth of the op-amp is infinite. So no matter what frequency my input signals are coming in at, they'll all get amplified by the same amount. So I don't have any 3 dB frequency associated with this. My gain, if I was to plot gain, or the transfer function for my op-amp, it's constant over all frequencies. Okay, so that's the ideal properties of my op-amp. Let's go back to this infinite open loop gain concept. Okay, so if I have infinite gain, that means that, let's say, here's my op-amp, and I'm going to get some output voltage. Let's say I ground that terminal, and I put in some input voltage. So does my voltage become infinity at the output? Because this gain goes to infinity. So let's look at the transfer characteristic. So infinite gain means that this is vertical, but I won't get infinite volts at the output because my amplifier is going to saturate. So I'm supplying this with some positive voltage and some negative voltage. So the maximum voltage I can get at the output is the same as that positive voltage. And the minimum, sorry, this is V negative. Minimum voltage I should get is whatever that negative voltage is. It does mean that this line, this transfer characteristic is completely vertical though. So as soon as I have any infinitesimally small input voltage, I'm automatically going to go to the maximum output voltage of my amplifier. That's what the infinite open loop gain means. Okay, but we never use an op-amp like this. We never use it in this open loop case. If you've seen op-amp circuits before, they always look, something like this, where I have a feedback loop from the output back to the input. Okay, so in this case, I don't have infinite gain anymore, but I do have a much more stable amplifier. It's much more predictable to use. Okay, so in the next lecture, we'll talk about adding these feedback loops to the amplifier and how it affects the performance.